This is Edexcel Further Pure 1 numerical methods, and in particular the midpoint method for first order differential equations. In the previous video we looked at Euler's method to estimate the value of a point somewhere further along the curve given a starting point x0, y0. So we used the point x0, y0 and the gradient at that point to generate an estimate for y1, the next value. And we had the generalized formula whereby we would increase x by a set amount, h, multiply that by the gradient at the current point to generate the value for y at the next point. But as the diagram illustrates, this may well lead to errors building quite quickly. So there might be another way of considering the gradient to improve our estimate. The midpoint formula is a way of generating a gradient to extrapolate from one point to another in a slightly different fashion, and perhaps more accurately, quite often more accurately than Euler's formula. So what we've got here on the diagram is that we're going to look for the gradient at a midpoint and use that gradient as being the average gradient between our previous point, xr minus 1 and yr minus 1, up to xr plus 1, yr plus 1. And you can see the step length here, the change in x is now 2h. So we're going to use the gradient at the midpoint to extrapolate from the previous point up to the next point. Now the difference between r minus 1 and r plus 1 is the thing that we're going to be estimating. So if we look at how we might write that gradient estimate down, if we take the gradient at r, and that's going to be approximately equal to our change in y. So we're going from yr minus 1 up to yr plus 1. So that's yr plus 1 minus yr minus 1, and divide that by the change in x, that's 2h. If we rearrange this to make the point that we're estimating the subject, so that's yr plus 1, is approximately equal to yr minus 1 plus 2h times the gradient of the midpoint. And of course, what you end up needing here is to know two y values to get the third y value. If you're only given one starting point on your curve, then to find the first value, you end up using Euler for the first value. And here's that written up more neatly for you to freeze the video if you want to. Notice that we are starting with r equal to 0. So actually the formula states we need to know the y minus 1 value. Of course, we don't end up needing to know the negative value if we start off using an Euler method. Just y0 gets you to y1, and then you can use y0 and y1 there, and you're starting off with r equals 1. If we look at the same function we used in the previous video for Euler's method, and we can use Euler's method to generate our first value, our value for y1. Now we're ready, having got two values for y. y0 is 1, y1 is 1.2. Now we need to work out what y2 is going to be. So if we take the general midpoint formula and we want to find out y2, so that means we've effectively got r equal to 1. That's going to be approximately equal to 1 minus 1, y0, plus 2h times the gradient at 1. So we need to work out what the gradient at 1 is going to be. So we can use our formula up here, dy by dx at 1, and that's the value r equals 1. That's not the x value 1 or y value 1. So we're using these two coordinates here to give us a value for dy by dx when r equals 1. So we've got 1.1 for x and we've got 1.2 for y. So our estimate for y2 is approximately equal to y0. Well, that is our 1 point, so that's 1, plus 2 times, and our x interval h is 0.1, and then we need to multiply that by the gradient of our function at r equals 1, which we've just put on the other side there. That's 1.1 plus the square root of 1.2. And here's that written up neatly, and the value actually calculated from a calculator. And as with Euler's method, the midpoint method improves with smaller intervals. And you can readily tabulate that with a spreadsheet. Here it is on the spreadsheet. And as a comparison, we can see using an interval of 0.1 using Euler's method, we got a value at 1.5 for x of y being 2.1959. But with the midpoint formula, we end up getting a value of 2.239. If you've looked at the previous video, when I reduced the interval to 0.05 rather than 0.1 for Euler's method, I got a value of around 2.22. So reducing the interval gave me a more accurate method using Euler, and you can see with the midpoint formula we have actually got slightly closer to an expected result as well. That was Edexcel Further Pure 1 Numerical Methods, the midpoint method for first order differential equations. Next up, second order differential equations.